3 kilometers below the surface of the ocean, in darkness where the pressure is 300 times what you feel at the surface, a steel drill bit is turning at the bottom of a hole. It is drilled through kilometers of rock to reach a reservoir of oil or gas that has been trapped there for millions of years. Above it, a slender string of steel pipe, thin compared to the forces it carries, stretches all the way up through the water column to a drill ship floating on the surface above. This is deep water drilling, and the physics involved make it one of the most astonishing things human engineering has ever attempted. Let's start with the scale of the challenge. When we talk about deep water, we're referring to water depths beyond 300 meters and ultra-deep water beyond 1,500 meters. The world record for deepest offshore drilling is over 3,400 meters of water depth. The actual well, the hole drilled below the seabed, can add another 6,000 to 9,000 meters of vertical depth. That means a drill bit more than 12 kilometers below the surface of the ocean. The vessel doing the drilling is a drill ship, a purpose-built ship with a derrick rising up to 60 meters above the deck, and a hole through the hull called a moon pool through which all the drilling equipment passes. A drill ship uses dynamic positioning, a computer-controlled system of thrusters, to hold itself precisely over the wellhead, without any connection to the seabed. In deep water, anchoring is not an option. The vessel must hold position to within a few meters, using GPS, acoustic beacons, and continuously adjusted thruster output. In rough weather, this can mean the thrusters are working flat out just to keep the ship still. The drilling process begins with a large diameter conductor pipe being installed at the seabed, the first structural element that defines the top of the well. From there, the drill string is assembled on the surface and lowered into the water. The drill string is a column of steel pipes screwed together, section by section, from the surface to the bit at the bottom. In deep water, the drill string can be 4 to 5 kilometers long before it even reaches the seabed, and then it continues down into the rock below. At the bottom of the drill string sits the bottom hole assembly, a collection of specialized tools including the drill bit itself, stabilizers, measurement instruments, and directional drilling tools. Modern offshore wells are rarely drilled straight down. They are steered, sometimes horizontally, through the rock to reach the reservoir at the optimum angle, maximizing recovery and reducing the number of wells needed. Directional drilling uses specialized motor assemblies and real-time telemetry that sends data from the bottom of the well to the surface. Engineers on the drill ship can see exactly where the bit is, what formations it is passing through, and adjust the trajectory accordingly, while the drill continues to turn thousands of meters below. As the well gets deeper, it is lined with a series of steel casings, large diameter steel tubes that are run into the hole and cemented in place. Each casing protects the well from the formation pressures encountered at that depth, prevents the sides of the hole from collapsing, and isolates different geological zones from each other. A typical deep-water well might have 4 or 5 concentric casing strings, each one smaller than the last, like a set of nested cylinders extending into the earth. Perhaps the most important piece of equipment in the entire deep-water drilling system, and the one that makes it possible to drill in deep water at all, is the blowout preventer, or BOP. A BOP is a stack of enormous hydraulic valves, typically 10 to 15 meters tall and weighing up to 400 tons, that sits on the seabed at the wellhead. Its purpose is to seal the well in the event that the well pressure begins to exceed what the drilling mud column can contain. If formation pressure surges up the wellbore, an event called a kick, the BOP can activate to shut in the well, preventing a blowout. The BOP is connected to the drill ship by a marine riser, a large diameter pipe through which all the drill pipe, drilling fluids, and equipment travel between the seabed and the surface. The riser is hung from the vessel and can flex to accommodate the vessel's motion. In the event of a critical emergency, the BOP can disconnect from the riser entirely and seal the well shut at the seabed, protecting the environment even if the vessel above is lost. The Deepwater Horizon blowout in 2010, in which a BOP failed to seal the well after a well control incident, released approximately 4.9 million barrels of oil into the Gulf of Mexico and killed 11 workers. It was one of the worst industrial accidents in history, and it fundamentally reshaped how deepwater drilling safety is regulated and practiced across the industry worldwide. Today, BOPs are tested more rigorously. Redundant systems are required, and real-time well monitoring is more sophisticated than ever. The technical standards applied to deepwater drilling equipment are among the most demanding of any industry on Earth. When a deepwater well is successfully completed, it is cased, perforated, and connected to the subsea production system, a collection of valves, trees, and manifolds on the seabed that control the flow of hydrocarbons from the reservoir through the wellhead and up to the production platform or floating facility above. That oil and gas then travels through flow lines and risers to the surface, where it is processed, stored, and eventually shipped to refineries around the world. Deepwater drilling is not glamorous from the outside. The rig is at sea. The well is invisible. The results appear at a fuel pump thousands of kilometers away. But beneath the surface, miles of precision engineering are turning, and the Earth is giving up what it has held for 100 million years.